Good day everyone, I am Meryl Shane Edelmonte and I'm going to present the Lagrangian and Eulerian descriptions under the fluid kinematics. But before proceeding with the descriptions, let me first introduce to you all what fluid kinematics is. Fluid kinematics is one of the branches of fluid mechanics which is concerned with describing fluid's motion without necessarily analyzing the forces responsible for such motion. It also provides a framework for describing and visualizing the movement of particles, which is crucial for analyzing and predicting fluid behavior in practical applications. There are two descriptions used to describe fluid motion, namely the Lagrangian and Eulerian descriptions. Lagrangian description follows individual fluid particles or collections of particles. It is named after the Italian mathematician Joseph Louis Lagrange. It also requires us to track the position and velocity of each fluid parcel, which we refer to as a fluid particle and take to be a parcel of fixed identity. There are many practical applications of the Lagrangian description. Some of those were tracking of passive scalars in flow to model contaminant transport, rarefied gas dynamics calculations concerning the re-entry of a spaceship into the Earth's atmosphere, and the development of flow visualization and measurement system based on particle tracking. As shown in Figure 1.1, with a small number of objects such as billiard balls on a pool table, individual objects can be tracked. On the other hand, Figure 1.2 in the Lagrangian description indicates that we must keep track of the position and velocity of individual particles. As you can imagine, the method of describing motion, is more difficult for fluids than for billiard balls, since we cannot easily define and identify fluid particles as they move around. Also, from a microscopic point of view, a fluid is a continuum, so interactions between fluid particles are not as easy to describe as are interactions between distinct objects like billiard balls. Furthermore, fluid particles continually deform as they move in the flow, as fluid is composed of billions of molecules that are continuously banging into one another. The other way to describe fluid motion is to apply the Eulerian description, which defines a control volume through which fluid flows in and out. This description was named after the Swiss mathematician Leonhard Euler. A finite volume called a flow domain or control volume is defined through which fluid flows in and out. Instead of tracking individual fluid particles, we define field variables and functions of space and time within the control volume. The field variable at a particular location and at a particular time is the value of the variable for whichever fluid particle happens to occupy that location at that time. As shown in the example, in the Eulerian description, all such field variables are defined at any location in the control volume and at any instant in time. To add, in this description, we don't care about what happens to individual fluid particles, rather we are concerned with the pressure, velocity, acceleration, etc. of whichever fluid particles happen to be at the location of interest at the time of interest. The difference between these two descriptions is made clearer by imagining a person standing beside a river measuring its properties. In the Lagrangian approach, he throws a probe that moves downstream with the water, while in the Eulerian approach, he anchors the probe at a fixed location in the water. There are many occasions in which the Lagrangian description is useful. The Eulerian description is often more convenient for fluid mechanics applications. Furthermore, experimental measurements are generally more suited to the Eulerian description. However, whereas the equations of motion in the Lagrangian description following individual fluid particles are well known, just like Newton's second law of motion, the equations of motion of fluid flow are not so readily apparent in the Eulerian description and must be carefully derived. We do this for control volume or integral analysis via the Reynolds transfer theorem at the end of this chapter. The material derivative can serve as a link between Lagrangian and Eulerian descriptions of continuum deformation. It computes the time rate of change of any quantity, such as temperature or velocity, which gives acceleration for a portion of a material moving with a velocity. If the material is a fluid, the movement is simply the flow field. The Reynolds transport theorem is used to study the behavior of flowing systems, such as the transport of momentum, energy, and other quantities through a fluid.